Okay, good morning, Aaron. We hope you feel better soon. That was not me. That was who you can guess, I'm sure. And you say they're your friends. Well, desperate people, desperate times. Okay, so what we're going to do is we're going to actually look at chapter 24 and chapter 25 reactions at the same time. And part of the reason for doing it is we did the chapter 25 naming out of order. And the other reason is that the compounds behave very similarly. Remember, we're looking at, in chapter 24, carboxylic acids that look like this, right? Well, we're looking at chapter 25 at amines that look like this. So they share a lot of the same functional groups and a lot of the same basic structure. And so we're going to see that a lot of the reactions between carboxylic acids and amides are the same. And if we take a look at esters, remember, that's kind of like a carboxylic acid, but it has an R group instead of that hydrogen there. Well, amides can also, of course, they're pretty flexible because they've got that N, they can actually have R groups also attached to them. And so amides and esters can also behave much the same. And so all of these compounds really are very similar. Now, I have to admit the amines, you know, they're going to behave more like alcohols when we see them in reactions, but there's not too many amine reactions. And so if we kind of group them up by mechanism of reaction, then we'll see that it doesn't really matter if we're doing in chapter 24 and then chapter 25. Really, my study guide and what I put on the web, it has chapter 24 and chapter 25 together because they're on the test together, right? And so I've got it all grouped on that by mechanism, whether it's a carboxylic acid or an ester or an amide, doesn't really matter because they're all mixed together. So actually, it might be better to lecture this way, to have like a day on naming, right? And then a day on the reactions, and then another day on all the miscellaneous topics, and maybe combine 2 chapters together. We'll give it a go. You guys are an experiment, right? I should also point out, since you, maybe I shouldn't say it on tape, but now I should go look at the information. But as far as like comparing your class with the class 2 years ago and last year's class and stuff, since they all had similar tests, all about the same. You guys are a little bit better. Just a little. So you got that going for you. Okay, so let's take a look at some review. And I say that this is review because we've had these reactions before, and that's the oxidation reactions. And the reason we care about the oxidation reactions is that's how we make carboxylic acids. We take a primary alcohol and we can oxidize it to make an aldehyde plus water. And then we can take that aldehyde and in a second step keep oxidizing it to make that carboxylic acid. And so that's review from both our alcohol chapter and it's a review from our aldehyde and ketone chapter. So basically the last exam. Do you guys want me to give you an example of that or anything, or are you guys pretty good on it? Heck, it's so easy to write the example, why not? Oops, I guess we'll show the plus H2O. And if we keep oxidizing that, we get our carboxylic acid. So hopefully on our, as you're studying for the test, you look at this reaction and you go, okay, I already know it, done. Don't even have to study it, it's just in my brain already. And so that's one less reaction you have to think about. The variation for that, if you guys remember, from way back when, this was in chapter 20. Actually, let's do it this way. You remember what happens when we oxidize things with benzene rings and R groups on them? So if we take benzoic, or if we take a alkyl plus a benzene and we oxidize that, what did we end up getting? So that was the reaction where we split it between the first 2 carbons and we ended up with benzoic acid plus then one other acid from that R group. And so we always got benzoic acid plus a carboxylic acid. And so sometimes reactions like these are lumped under the name formation reactions because these are the normal paths for forming carboxylic acids. The easiest way to make a carboxylic acid is to take an alcohol or an aldehyde and oxidize it. Another way, especially if you want to get some benzoic acid, is just to take any benzene ring with an R group on it and oxidize it to benzoic acid and whatever other carboxylic acid you're getting. So hopefully those are review reactions because those are oxidation reactions that we already know. We also have some reduction reactions because we said oxidation and reduction are always paired. And so we have two reduction reactions. We have an amide can be reduced. And actually, let me look and see. How do I normally write that arrow? I think we just, I can't remember if I switched. Yeah, you're right. I did do the H2NI still because I was being consistent. Meaning in the book, they kind of flip-flop back and forth and they use different things for showing reductions. I'm trying to standardize it. And so this generally makes an amine plus water. And if you think about it, it sort of makes sense. An amide has lots of bonds to oxygen, and if we lose those bonds to oxygen, that means we are oxidizing something, right? And we're also gaining, if we lose the bonds to oxygen and we gain bonds to hydrogen, that means we're reducing something, right? So if I take an amide, and we'll make the sides different so it's pretty obvious. And we've got our hydrogen gas and our nickel and our heat. Now, what do we say about reactions like this? I mean, we can memorize that amides get reduced to amines, but really, reductions like this are usually adding hydrogen across that carbon-oxygen double bond, right? Just like we did when we reduced primary or aldehydes and ketones back to alcohols, right? And so we can think about it as I'm adding a hydrogen here, and I'm adding a hydrogen here, and then we actually add a second hydrogen to both sides. And it's really a two-step process, but you know, for the results on the test, we're simply going to show it as a one-step process. So there's my NH, and then see what I've really got is I've got two hydrogens that were added to this carbon right here, right? Here, let's get rid of that. So we're talking about the same carbon, we're paying attention to it. And then notice that we get plus H2O because on the top part, I'll have H2O, right? By adding two hydrogens to that oxygen. So I very definitely lost two bonds to oxygen. I gained two bonds to hydrogen. Therefore, we consider that a reduction. And we could, if we wanted to, follow where the electrons are going in all these reactions, but that sounds like a lot of work when we don't really care that much about it yet. And very similar to an amide is if we take a nitrile and we reduce it to an amine. And in this case, we don't end up with water because if we take a look at a nitrile, you guys remember what that functional group is? It's a carbon triple bonded to a nitrogen, right? And so if we're thinking about adding hydrogen to that, we're going to add a hydrogen to the nitrogen, or well, let me show it consistently. I'm going to add a hydrogen to the carbon, and I'm going to add a hydrogen to the nitrogen. I'm going to add a hydrogen to that carbon. I'm going to add another hydrogen to nitrogen. And so what I really end up getting is a single bond to nitrogen. There's my hydrogens, there's my hydrogens, and of course the nitrogen has two hydrogens attached to it too from that reaction, and so I get a amine. And if we want to be really specific, I get a primary amine. Although, frankly, I just think if you remember that it's an amine, you'll get the right answer. And again, notice that we obviously gain bonds to hydrogen. And in fact, we gain 4 bonds to hydrogen on that molecule, right? Because we gain bonds from the nitrogen to the hydrogen and the carbons to hydrogen, and therefore it's reduction. And notice that in this case, we don't lose any bonds to oxygen because, well, there's no oxygen in the reaction. So these are reduction reactions, but I have to be honest, I like to kind of think about them as additions instead. Does that make sense to you guys? And so, you know, if the book calls them reductions, someone else calls them reductions, but you remember that you add hydrogens to both sides of the double bonds in the carbon-oxygen part, and you add hydrogen to both double bonds in the nitrogen, or the triple bond, I'm sorry, in the nitrile, then you probably kind of got it down anyway. Okay, so that's oxidation and reduction. You guys okay? Okay, one of the properties that we want to kind of think about is that carboxylic acids are acids, right? What does it mean to be an acid? What? Remember, acids donate protons, right? Or H+ ions to water. So what we're saying is that if this reacts with water, we can either think about it like this, where, you know, we just have it have a negative charge plus HOHO. And remember, that has a plus charge. We call that the hydronium ion. Right? Or we can have a carboxylic acid plus a base. And what do we have when we have acid plus base? Remember, acid plus base goes to, from first semester, please, salt plus water plus, of course, heat, right? And so notice that if I do that, I get a carboxylic acid salt O minus Na plus. So here's my carboxylic acid salt plus HOH plus heat, since we know that. So carboxylic acids, the word acid is right in the name, you know, should make it pretty obvious that it behaves as an acid. And what that's going to mean is that it behaves differently in acidic versus basic solutions. And for our purposes, what we're going to say is an acidic solution means if I've got HCl hanging around the reaction, and in a basic solution that means I have NaOH. But really, HCl could be any base, right? Or I'm sorry, any base. HCl could be any acid. What are some other acids you were supposed to remember from first semester? Yeah, oh my God. Nitric acid, like HNO3. And certainly we can have phosphoric, sulfuric, acetic. We could have, in fact, should point out, what is acetic acid? You guys remember it was this, right? That's just a carboxylic acid, right? So acetic acid is really just a carboxylic acid. We always wrote it as C2H3O2H, or sometimes they write it as CH3COOH, but that's kind of an aside. So acetic acid is really actually a carboxylic acid in this case. And then we've got like HF, HBr, HI. Now, we could mix those all up on tests and everything else, but we're going to just stick with HCl. What are some other bases that we remember? Anything that's in that column with Na, right? Boy, you guys are forgetting the periodic table already. Maybe we'll have a quiz on the periodic table. Extra credit quiz? Everything's extra credit. I'm just going to have, I should just do that on my syllabus next year. Be like, this is an extra credit test. This is an extra credit homework assignment. This is an extra credit everything. Everything's extra credit. But you also start at minus 1,000 in the whole. So you have to do extra credit to pass. Anyway, so basically KOH, magnesium hydroxide, barium hydroxide, lithium hydroxide, all those would be other examples. Well, we're going to stick to it with NaOH. And so what that means is that if I have a carboxylic acid, and I'm not saying I'm adding a carboxylic acid plus an acid, but I'm saying that if I've got a reaction with a carboxylic acid and an acid in place, then we normally just make a carboxylic acid someplace in a reaction. And if I have a carboxylic acid, but I have a base like NaOH, then I almost invariably make a carboxylic acid salt with that sodium, and then something else. So when you see carboxylic acids, if you see sodium around, what should you automatically assume? Salt. Yeah, it makes a salt. Same thing with amines. There are bases. And so they can interact with water to make a base. So for instance, if I take an amine plus water, I make an amine cation plus OH minus. Or if I take a look at that in the form of a reaction, if I've got an amine plus water, what really happens is that amine has a lone pair of electrons, right? And so that lone pair of electrons is certainly attracted to that hydrogen. And so we get an NH3 plus, where that extra hydrogen is now on my amine, plus that OH minus group. And so because it produces OH minus in solution, therefore it's a base. So carboxylic acid chemistry and amine chemistry are more complicated to a certain extent in that depending upon whether your solution is acidic or your solution is basic, you might get a carboxylic acid or you might get a carboxylic acid salt. And we're going to see that the same thing applies to amines. You might get an amine or you might get the amine salt in the reaction. And the way the salt forms generally is if I take an amine, let's write it out in words first. I like words sometimes. An amine plus an acid goes to an amine salt. And of course, when we say acid, what do we mean in this class, just to keep life simple? Yeah, HCl. But you can draw and write all the same reactions with any of the acids. It looks a little strange sometimes because, I don't know, I'm so used to using HCl because I like to keep life simple that I sometimes get tricked. So what happens is I make that NH3 and then I've got a plus sign and then that pairs up with the minus sign. And so this is called an amine salt because, well, it's got a plus and a minus. It's an ionic compound at that point, or that part of the molecule is ionic. It's similar to if we think about NH4Cl. Remember we said that that's a plus and that's a minus. And so a lot of times these are called ammonium salts because if there's no R group, then we really do get ammonium chloride, and sometimes they're referred to as amine salts. And so when you're kind of reading in your book, if you see that it forms NH4Cl or if it forms the amine salt, it's the same process in the reaction. It's just whether there's an R group attached to that nitrogen. So when we see sodium in a reaction, we should expect to form carboxylic acid salts, right? Oops, sodium leads to carboxylic acid salts someplace. And chlorine leads to amine salts. And if we see sodium plus chlorine in a reaction, what should we expect? NaCl, right? Because we know that sodium and chlorine love to get together and make salt. So with those simple rules applied to some of these reactions, it's a lot easier to keep track of what's going on. And so there's a two-step process. You're going to have to kind of remember what's going on in the reaction, but you're also going to have to throw on that added thing of every time we show the reaction, we can usually show it in acidic, basic, and neutral solutions. About the same thing is happening in all of them, but the thing that changes is some of them we form a carboxylic acid or we form the salt. In some reactions we're going to form an amine, and some we're going to form the amine salt, and in some we'll actually form sodium chloride. And so what I want you to be aware of is that if you remember this rule with the sodium and the chlorides, then when you start looking at all those reactions that kind of look complicated because there's a lot of stuff going on, they get a lot easier because you know to expect the salts. So let's take a look at a bunch of reactions. So, well, actually, let's go a little different order than I had planned. Let's review dehydration, because that's the one you're familiar with, right? What do we normally see on the arrow? Minus H2O. And so the first one for this, there's three of them, is one you've seen, a carboxylic acid plus an alcohol. What does that make? That made an ester plus water, right? And so if I had a carboxylic acid plus some alcohol, and again, this one I consider review. We've had it before, so hopefully when you're going through your list of things to study, you're like, done it, been there, don't even have to worry about it. So far, like half the reactions we've done, hopefully are reviewed. So remember, if we've got two OHs present, we go, okay, take an H and an OH, and that means I need to connect that carbon with that oxygen, because that's where I broke those bonds. So I make my carboxylic acid plus my HOH. And if we want to blow that up, maybe to make it a little more obvious what's going on, because sometimes I write a little small, sometimes I am in a hurry, so I want to skip some steps. What we're saying is that if I break this bond, that leaves an electron on that carbon. And if I break that bond, that leaves an electron on that oxygen. Now, correspondingly, it leaves an electron on the hydrogen, and it leaves an electron on the oxygen. And so the HOH, of course, is formed pretty easily because those two electrons pair up and make water. So really what we're saying is that the new bond we make is that, right? And then the carboxylic acid part is the same way. I've got this oxygen. It's got a lone electron. It pairs up with that lone electron on that carbon. And so we get something that looks like that. And then, of course, remember, I'm kind of using those as lone electrons now. And so that really is forming that new bond. Oops, can't have. So, there's that electrons that got together. So, like I said, if you can remember the mechanism, when you see two waters, or when you see a dehydration or two waters, or OHs, and you break it apart, if you show where you break it apart, those are just the pieces that get connected together, right? It's kind of like if if you really took those models that we have apart, right, you could just pull the model apart and plug the two pieces together. And heck, if you want to use the models for reactions, feel free. Okay, similar to that reaction is a carboxylic acid plus an amine. And see, here's what's nice. If you kind of think about it, carboxylic acid plus alcohol is very similar to carboxylic acid plus amine, because amines and alcohols are very much alike, right? And so we should expect to make an amide instead of an ester plus water. And so again, here's my carboxylic acid. Let's make it a big amine so that there's differences. And so here we have to lose the OH on the carboxylic acid, and we're losing one of the H's on the nitrogen, or I'm sorry, on the hydrogen. So here's where my breakage occurs. So that means I have to connect the nitrogen and the carbon together to make my amide plus water. So if you ask me, that reaction is exactly the same as the past one. Meaning, if you can link that up in your head that carboxylic acids plus alcohols and carboxylic acid plus amines both lose water, and really, do you have a choice of where you get the water from too much? I mean, I guess you could try to take that carbon double bonded to the oxygen, but that doesn't happen very often. It does in some reactions, but not very often. Okay, and then the third one is if I take a carboxylic acid plus a carboxylic acid, and I lose water, I get what's called an acid anhydride. What does the word anhydride mean, or anhydrous, if you hear that word occasionally? Simply means without water. So an acid anhydride is a bunch of carboxylic acids without water, and of course you have to get plus HOH, right? And this reaction kind of comes back in chapter 33. This is the reaction your body uses to kind of make what are called activated carboxylic acids, meaning they're going to go on in another step or in another process to be used. It's also similar to, but not quite like, what we're going to talk about when we make phosphate anhydride bonds, or you guys have studied ATP in biology certainly, right? Talking about making ATP and doing some of the reactions there. And so this reaction, it's kind of similar to that, and so we'll see it again. So here's a carboxylic acid, and here's another carboxylic acid. And it doesn't matter which one you take the OH from and which one you take the H from. What you have to do is connect that oxygen and that carbon. And so I get a carboxylic acid, and then I get an oxygen, and then I get another carboxylic acid. And I always think that these reactions look like little crabs once the R groups on either side get big enough for some reason. This one's kind of stunted, right? He's only got a short arm on one side. But, I always think that that looks kind of like two eyes and a mouth, and maybe I can put a nose in there. I don't know. Some eyebrows. Looks like a little person, kind of, doesn't it? Okay, maybe I'm the only weird person that does shit like that. I don't know. So here's my hope. As we're going through this, I hope you're saying, dehydration, let's move on, Jay. This is too easy. And if you're not, that's fine. We can certainly keep going through things like this, ask questions on it. But if you're learning things by these mechanisms that we've been talking about, then hopefully you start to see the patterns. And once you see the patterns, it's pretty easy to apply them and to kind of remember what's going on. And the reason I wanted to cover dehydrations real quick is, before I go on to the next group, is really, even though I have them reversed in my notes, it makes more sense because what we're going to talk about next is the opposite of dehydrations. What's the opposite of a dehydration? It's called hydrolysis, and we really do add H2O, and what that really ends up doing is that breaks apart molecules. I should point out, and I maybe should have made more of a big deal of it earlier too, breaks apart molecules. Finish my sentence first. Yeah. We're actually going to break bonds. So we're actually breaking things, not just, intermolecular forces. So in the biochemistry chapters, the number one reaction that we see most often is dehydration to put two small molecules together, and hydrolysis to take a big molecule and break it apart. So if you have to remember two of the reactions from organic chemistry, remember dehydration and remember the hydrolysis reactions. We're going to keep coming to those over and over and over again, okay? And we'll also be using all the functional group analysis that we've had. We'll be coming back to other types of reactions too, but these are like the big two. So water breaks things apart. So if I have an ester plus water, now here's what's going to change. What's on the reaction arrow can be totally random and changes constantly. What's always the same is the plus H2O part on the reactant side now. So in this case, we might have hydrogen ions. Now, The other nice thing about hydrolysis reactions is, since they're the opposite of dehydrations, what do you know an ester has to break apart into? Yeah, what reacts together to give an ester? Carboxylic acid and alcohol. What does an ester break apart into? A carboxylic acid plus an alcohol. So the other nice thing about hydrolysis reactions, and I have to be honest, they're a little bit more complicated than just your basic dehydrations because of that whole acid-base character of the carboxylic acids and the amides when we get to them. But they're always the opposite of the dehydration reactions for the most part. So if you've got those dehydration reactions down pretty good, you can figure out what happens in the hydrolysis reactions. It's kind of like the oxidation reduction reactions in that they're opposites too. So if I show this as an example, here's my ester, here's my water. Notice that I'm already showing the water with that bond so I can break it apart. Maybe I'll even emphasize that. We'll make it bigger. Now, the trick with hydrolysis reactions is you have to figure out where the molecule breaks apart. But that's not too hard. It always breaks apart right at that oxygen right there. That's where my break occurs. And it doesn't really matter for the most part whether you break it on the right side or the left side, as long as you realize when you break it, when I add my water, I'm adding my water like that, right? And so the hydrogen goes to one side and the OH goes to the other side of my break, and I get my carboxylic acid plus my alcohol. Now, please do note that, for instance, here, I kind of put the alcohol group on the other end, right? Meaning, whether I write it like that or I make it like that so it's a HO group instead of an O group, they're both the same molecule, right? For whatever reason, when I draw stuff, I tend to put the functional group on the right-hand side. I don't know why. Probably because I'm too busy counting carbons at the beginning of it and going, oh, I need 3 carbons, 1, 2, 3, and then a functional group, instead of going, let's draw the functional group and then count carbons. It's just my habit, which arguably in this case, it probably makes more sense to show it like this, right? Because that really is the orientation that it was facing in before, or the orientation when those molecules break apart. So an ester plus alcohol, or plus water, is going to give me a carboxylic acid plus an alcohol. And that's in the hydrogen, or if I have acid present, right? Because remember, carboxylic acid is already an acid. If there's acid present, it's just going to stay as carboxylic acid for the most part. We have a very similar reaction to this. It's called an ester plus NaOH. Now, since I've got sodium around, instead of making a carboxylic acid, what do you think I'm going to make? I'm going to make the carboxylic acid salt plus alcohol. Because if the sodium's around, then the carboxylic acid makes a salt. So again, if you can keep that rule with sodium around, or in the back of your head, sodium means carboxylic acid salts, chlorine means amine salts, which we haven't looked at yet. I should also point out that these reactions have other names. Sometimes this one, which one is which? Let me double check. I don't want to give you this one. Sometimes we call this, oh, that one's a hydrolysis. If it's with a base, they sometimes give the special name of saponification. Saponification. Whatever, I don't really care. I'm not really going to say things. But if you read in your book and it says, this is a saponification reaction, realize it just means that I used sodium hydroxide to break it apart. It's the exact same thing as a hydrolysis reaction with sodium hydroxide. So again, let's have an ester. And then I've got my NaOH. And notice, I'm kind of being a little silly. Am I kind of showing the NaOH with a bond, right? But, oops, actually I showed it the wrong way. NaO-H. Because that's how our sodium hydroxide is going to break apart. Well, actually it just depends on either way you want to look at it. It really, Here, let's just do it like this, because it really doesn't matter. The idea is that the sodium is going to go there, and the OH is going to go on that side of the break. Why I'm saying it doesn't matter is because, like I said, you can break it on the right-hand side or you can break it on the left-hand side, and either way logically kind of makes sense. So in this case, then I get my carboxylic acid, but I've got a Na plus next to it. And then, of course, I get my alcohol just like before. So the only difference between this reaction and the water reaction is whether I make a carboxylic acid or I make a carboxylic acid salt, right? You're going to see the same thing when we do a lot of amide reactions, in that it doesn't matter if I have whether I make the carboxylic acid from the reaction or I make a carboxylic acid salt and an amine. So esters plus water or esters plus sodium hydroxide, just break them apart. Okay, we have the same reactions, but we can do amides, because we said that amides and esters are much the same. So an amide plus an acid plus water, and in this case we have to show the acid because we know that when I have a chlorine around, or when I have that anion from an acid around, I make an amine salt. So this goes and makes carboxylic acid plus an amine salt. See, amines are different than alcohols in one respect, in that even though they have the same sorts of reactions and stuff, they tend to make those amine salts. We tend to not make alcohol salts. The reason for that is, remember, the hydrogen bonds in amines are weak, right? The hydrogen bonds in alcohols are strong, comparatively speaking. And so that means that amines and alcohols, while they behave a lot alike sometimes, also sometimes don't behave alike. So if I take an amide, plus an acid, and our favorite acid is HCl, of course, and H2O. Actually, let me draw the water like it's supposed to be. Let's see. In my notes, no, doesn't look like it. I got to be honest, like I said, whether something's on that arrow or not, what I focus in on is the HOH. So a lot of times I'll forget what's on the arrow. That, and like I said, a lot of times depending upon the book you look at, they might put things in different spots. Some books might show the HCl and the water on the arrow too for some reason. It's very books dependent on things like that. So I'm going to break my water apart. I'm going to break that apart. So here's my OH and my H, right? Does that make sense? So there's my carboxylic acid. And then what happens is, the reason the HCl is there is that also, both parts react with the amine. So we showed earlier that an amine plus an acid, that's kind of like an acid plus a base, goes to a salt. And so in this case we get the amine salt, and so I have a plus sign and a minus sign. And so you can kind of think about them as two separate reactions, in that we make first the carboxylic acid and an amine, and then amines automatically react with any acid to make an amine salt.
Can you break it instead of in front of the ends for the NH on the left side? Can you break it after the H?
No, because then the N would be stuck on the carboxylic acid, which it really isn't. So here in this case we have to break it on the left side. And in fact, that's one of the things I'm going to write myself a note. Always break it on the left side, mostly because then that's the same for amines and alcohols. So there really is a preferential side. I just always forget which side until I do the amines. Does that kind of make sense or not? So remember, what I'm saying is if you can remember that this reaction is the same as ester plus acid plus water, for instance, you can kind of think about it as that normally makes a carboxylic acid plus an alcohol, but instead of an alcohol, we're going to make an amine, right? And because amines form salts with acids, in the acid conditions, we form that carboxylic acid like that. Okay, what do you think the next reaction is going to be? What? Well, if I broke apart an amide with an acid, the next logical step is to break apart an amide with a base. So we have acid hydrolysis and we have base hydrolysis. So this is kind of a two-step reaction, generally. And we can break it apart into the two steps. The first step is, oh wait, am I in the wrong one? Never mind, I'm thinking the wrong thing. I lied. Give me a break. Do you want to take a break to get more coffee?
No.
Oh, maybe. I've only drank half my cup. An amide plus sodium hydroxide is going to make, here we expect to make the carboxylic acid salt, right? Because we've got the Na plus then an amine instead of the normal alcohol. So we've got our amide plus our sodium hydroxide. We break it apart right here. We break it apart right here. And so we get our carboxylic acid salt, O minus, Na plus, plus just our, oops, that's an H, our normal amine. There are, I don't even know if I should point it out ahead of time. Oops, I'm sorry. I forgot to put the arrow in. Good call. One of the things that I know people have difficulty with, especially when they first learn these reactions, is sometimes we write NH2, sometimes we write NH3, sometimes it is a plus charge, sometimes it doesn't. So let's put it this way. Nitrogen is supposed to have 3 bonds, right? Notice it has 3 bonds there, right? 1 to the carbon and 2 to the hydrogens. So if it has 3 bonds, it's just NH2 or whatever it is, right? If we add a 4th bond to it, so if that suddenly becomes like NH3, then that means it has to have a plus charge on it, and that means it has to be paired up with an anion. And so if nitrogen has 4 bonds, it forms a salt. If nitrogen has 3 bonds, it just forms whatever amine it's normally hanging out as. Yes, no? So NaOH goes on this side of the reaction. That hydrogen is going on that side. So bless you. So you guys okay with me? We're cruising along pretty well. The thing is you're going to have to sit and you're going to have to practice these reactions. You're going to have to look at a whole pile of shit on the left-hand side of a page, right, where it's just reactants, reactants, and reactants over, and start logically going, okay, where am I going to start? Maybe you're going to start and say, let's just do all the oxidation ones because that arrow is really easy, right? Then you're going to say, let's do the reduction ones. They're a little bit new, but that arrow is easy to pick out, right? Then you're going to say, gosh, let's do all the dehydration ones because that arrow is easy to pick out. And then by the time you get to that point, you're going to be saying, okay, well, now I'm left with the hydrolysis reactions where it's either plus water or plus NaOH on the left-hand side or some HCl and water and stuff. And then you can start doing those. But work through it systematically. Realize that the homework's all mixed up. The practice sheets are all mixed up. You don't have to do it in the order that it's written in, do you? You can do it in whatever order you want. You're adults. Well, it's where you break it. Plus, it makes no sense to have something like this to a certain extent because sodium is not going to form a bond with, we don't make metal carbon bonds. because that would be a metal, nonmetal, so that should be also ionic, right? And so that means that if I was really going to make a bond like that, this carbon here should have a plus sign, or would have to have a minus sign, and then it would have to be an Na plus. So we can make carbon-oxygen bonds because they're both nonmetals, right? So if we look at this, this is nonmetal for that bond, and it makes sense. It's a good question. It's not one I think about because to me it's like, duh. Meaning, you know, it's something I do all the time. For you guys, that's a good question. So yeah, it's always going to have that O attached to the oxygen because that's an organic bond. It's a non-metal. They're sharing electrons. And then the sodium bond. Because you would never have something like a minus, a sodium plus, and then an O minus. There's just, the charges don't add up or balance. You'd have to have another plus charge someplace there. Does that make sense? Okay. So that was an amide plus sodium hydroxide makes a carboxylic acid, salt plus an amine, right? Okay, we have one last set that are similar to this. They're hydrolysis reactions. I lumped them together, but they don't follow the same pattern as the other 4 reactions. Yep, that was 4 of them in a row. So you can have an ester plus water, an ester plus sodium hydroxide, an amide plus water, or an amide plus sodium hydroxide. So the last set are for nitriles. And I got to be honest, these are now, they're not complicated to do, meaning they're not complicated for you to learn necessarily, because you can just memorize them. But they are a 9-step process. Oops, whatever. I don't care if that's how you spell process or not. I'm serious. I sat down yesterday because I had a little bit of free time when I wasn't grading and writing your tests and various things like that, and said, you know, I always make my class memorize how to do this. And I'm like, that sucks. And, oh, I mean memorize the reaction. And then I said, maybe there's some process or a couple steps we can use to make it make more sense. And so then I started looking at it, and I tried to come up with a fake one, and that doesn't work too well. Then I looked up on the internet how to really do it, which is 9 steps for one of the reactions and like 5 or something for some more. And then I finally just said, you know what? They're just going to have to memorize this reaction because no one wants to learn all the steps to it. I don't even want to learn all the steps to it. And so I wanted to make it easier and have something rational, because I think, like, for instance, the dehydrations make sense, the hydrolysis make sense for the most part, and things like that. This reaction, not so much. So, nitrile plus 2H2O. My hand's over it. I tell you what, if you want to test me on this shit, go ahead and write one down on a piece of paper and bring it to me at a random time during the day. And I have to be honest, even on these, I'll have to think really hard about it. And here's the trick. I won't remember it based on words. I'll have to draw a picture, because that's how I remember things. I draw. For this, getting the words right kind of sucks. I know it makes a carboxylic acid. And here's the other thing, advantage I'll have over you. What's every one of these hydrolysis reactions made? Some sort of carboxylic acid. See, that's the things that, well, here's where I think teachers help. If you just had to read these 6 reactions in a book, if they pointed out that they always make carboxylic acids, that might be useful. But most books just say, here's a bunch of shit in reactions, and it's up to you to start looking for patterns. I hope that by telling you guys some of the patterns, I make it easier for you guys to learn it. But in the end, it always comes down to you've got to find the pattern. You've got to find what's going to trigger your brain to do a specific type of reaction. And then, of course, if it's making a carboxylic acid salt, or I'm sorry, not a salt, if it's making a carboxylic acid, we still got some nitrogen around. That means it's going to have to make some sort of amine. And in this case, because I've got the HCl, that means it's going to make an amine salt. So remember, chlorines make amine salts, sodiums make carboxylic acid salts. Amine salts, sodiums make carboxylic acid salts. So when you see a chlorine in a reaction, make the amine salt. If you see a sodium, go ahead and make the carboxylic acid salt. So here's how I'm going to, well, here's how you're going to see the reaction. And here's the end product for the reaction. Let's talk about how you get there. Oops, I lied. I was showing you the next reaction. I wasn't thinking. Well, here's one of the things that we have to be careful of. See, there's no R group attached to that nitrogen, so I can't make some random amine. So I've been making some random amines like 5 times in a row. So notice that this amine salt is really an ammonium chloride in this case specifically. But that if we had something else attached to that end, we would end up making an amine, although we don't see it. So the way I think about this reaction is that I'm breaking that or that triple bond to nitrogen by adding, say, water like this. So there's a water, right? And then I add another water like this. And then I add some HCl because amines or ammonia always reacts with the HCl to do it. And so I don't know how you want to think about this. Like I said, it's a friggin' hard reaction. It might be the easiest to simply memorize that nitriles get reduced or get hydrolyzed to carboxylic acids and amines. That might be enough for you to figure out what's going on. It might be good that you kind of think about how all these stupid waters get broken apart. I don't know. It's a tough one. And so if I do that, notice that I've got a double bond oxygen on top. I've got an OH on bottom. I've got a nitrogen with 1, 2, 3, 4 hydrogens. That means it's got to have a plus sign since it's got 4 bonds. And then, of course, I make the salt with the chlorine. So the water should tell you that you're making or doing a hydrolysis reaction. All these things hydrolyze to give a carboxylic acid plus something else. See, if nothing else, if you keep track of all the parts, you can figure out the something else part usually pretty easy too. So, we're breaking that bond. We're breaking that. Okay, the last one is a nitrile, or the next one I should say, plus H2O plus sodium hydroxide. And in this case, I'm not going to make the carboxylic acid. I'm going to make the salt. Actually, let's just highlight the salt part because that's what we care about. Because we've got the sodium plus ammonia. And so I've got my nitrile plus H2O plus NaOH. I get my carboxylic acid salt plus, in this case, just NH3. And the reasoning for this is that remember, it's NH, or it's a nitrogen with 3 bonds to stuff, then it's just, what it is, right? And if it gets that 4th bond to a hydrogen or a 4th bond, then it makes a salt. Plus, is there any chlorine around to make a salt? No, so it can't be the salt. And so again, if you're trying to think of a mechanism, and like I said, these reactions, I think the first one is a 9-step one, and when I looked at the next one, that one was a bunch of steps too. So again, we're thinking I'm going to add my O and a couple H's. I'm going to add my NaO and an H. And so I'm breaking it all apart to make that double bond up there, the O minus, the Na plus the NH3, if you kind of look at how things are grouped. I sort of apologize for these reactions because, quite honestly, I can't think of an easier way to teach them to almost memorize them or to figure out where all the parts are added together. The actual mechanism, like I said, is 9 steps. And it involves breaking many bonds and making many new bonds. and just, it's ugly. And it really, the only way to understand this reaction truly is to really do organic chemistry, which means you start memorizing the 6 different standard mechanisms for organic chemistry. And even at that point, I've never met anyone that really understands it all. I think they just memorize it all. Organic chemistry is tough. If I had to pick the toughest class I had in school, I would say it was organic chemistry personally. Sometimes wish I could go back and retake that organic chemistry with some of the knowledge I have now about how to study and how to think about it, and maybe it would have been a heck of a lot easier. I don't know. My organic chemistry teacher basically just would be like, here's a reaction, here's a reaction, here's another reaction, here's a third reaction, here's a fourth reaction. He may have honestly said, you need to remember these reactions by this, or here's some mechanisms that you should learn. I don't even remember, it's been so long. All I remember is having to memorize lists and lists and lists of reactions. Hopefully you're remembering things like dehydrations and hydrolysis and the mechanisms involved too. I hope. And actually, I would expect if I see all of you guys on campus in the dental hygiene program next year, that if I said anything to you, you would, about organic chemistry, like, what's this do? You'd be like, you know, like that, or something. Punch me in the face, whatever. Okay, we are going long today. Mostly because I want to get all the reactions down on paper. I want you guys to try them all over the weekend. And then on Monday, we'll go through and answer questions and review them and do lots of stuff like that, okay? So really, I'm just trying to get it all out there so you have a chance to look at it. Because if I try to break it up into multiple parts, it doesn't make sense. So we've got technically 4 more reactions. Now, maybe I could just stop here. I don't know. It's up to you guys. And when you're doing your homework, you're just going to have to skip some of the reactions. But if we do that, then that means on Monday, I want you to finish the homework Monday afternoon so that on Tuesday you can turn it in. Well, it depends on how you count, but 1, 2, 3, 4, 5, 6. And actually, I'll show you one more here just because it's paired with this a lot. If we see a carboxylic acid salt a lot, and technically the second step to this reaction is anytime you take a carboxylic acid salt plus an acid, maybe I should write that, you get a carboxylic acid plus an ionic salt. And what that's really saying is that if I have something with sodium and I have something with chlorine, I always make NaCl. You guys remember that from the last chapter, right? Sodium and chlorine love to make salt. And so this reaction is not too bad. And what it really is it's the finishing step to this previous reaction in that we generally want a pure carboxylic acid. And the way to get pure carboxylic acids is to simply react them with another acid so that I get carboxylic acid and I get NaCl. So remember, sodium by itself, carboxylic acid salts. Chlorine by itself, amine salt. Sodium and chloride together, NaCl. You guys want to stop or not? I kind of feel like stopping. So the reactions that you're not going to be able to do are amines plus acids. And there's one that uses something called SOCl2, which is called thionyl chloride. Just skip it. Obviously, we haven't even talked about it, right? And there's one other one where we have 2 amines plus an acid halide. And again, you won't know how to do it. So go through your homeworks and do that. And I have to be honest, to a certain extent, I could care less if you do the homework or not. If you want to do the practice sheets instead, I mean, I would say do the homework anyway, but you know, you're going to want to be using those practice sheets too. 24, so let's say what's going to do. So what I want you to do is homework 24 and 25. You guys are going to tell Taylor this, right? 24 and 25C are due Monday. Meaning get them done. And then 24B and 25C are due 75% of it. Oh, that's a B. See, we kind of are doing these chapters in parallel instead of sequentially like we have in the past. God bless you. And so what we'll do on Tuesday then is we'll say that 24B and 24C are all due. And then we'll have a really good review. We'll get everything straightened out. Wednesday, we're going to start in on stereochemistry. Thursday, we're going to have a test on 24 and 25. And it seems like it's coming really fast on that old test, right? And the reason for that is we stretched out some of that material on that last test. I think it was worthwhile to stretch it out a little bit because you guys did really well. And this test, I don't feel too bad doing here because so fast, because this is all stuff you're used to. The only thing that's really new is a tiny little bit of naming, not very hard. You guys are getting good at that. I think there was only 1 or 2 people that missed more than 1 name. So that was good. And then the reactions, yeah, they're new, but a lot of them are mechanisms you already know. And so you're capable and you know how to learn and study this material. And then on Friday, we party.
Can we not have class?
I think we have class. I think the following Friday we don't have class. I think I should look on my schedule. Whatever the first Friday in March, I won't have class. So I think we have class this next Friday, but the following one. If it turns out to be that, that's rather convenient for you guys.